Today, we're honored to have Akari Asai. He's currently a research scientist at AI2 and will be joining CMU as an assistant professor in fall 2026. And so she's a world expert in this area of retrieval-augmented generation. He had some of the earliest work in the area and really impactful work like self-RAG. And recently, she led the development of OpenScholar. It's a system for literature review that preceded today's deep research systems. And we actually saw a demo of it in the very first lecture of the course. And recently she was named to MIT Technology Review's 35 Innovators Under 35 for her work on retrieval augmented generation. So she's perfect person to give this lecture today, and I hope everyone learns a lot from it. So with that, please take it away.
Yeah, thank you so much for kind introduction and inviting me to give a lecture today. And hello, everyone. I'm Akari. I'm a research scientist at Allen Institute for AI, and I will be assistant professor at CMU starting next year. And I'm really excited to talk about retrieval and retrieval-augmented generation today, which I believe one of the most impactful and important area of language models in today's world. And feel free to interrupt me anytime or to ask questions or post questions in Zoom chat, and I try to answer them during or after the lecture. Okay, so let me start. Oh wait, sorry. Let me check. Okay. So to understand why retrieval-augmented language models are so powerful and widely used, let me briefly remind you how normal language models are built today. Their training involves two main components, massive pre-training data and the language model itself. Oh, so should I minimize the chat?
We can't see it on the screen.
Okay, we can just keep it.
And then if someone posts a message, I can
Okay.
at some point.
Okay, sounds
Good
good.
question.
Okay. Okay. Let me. Okay. Yeah. So their language models pre-training data. Language model pre-training involves two main components: massive pre-training data and the language model itself. And during pre-training times, documents like ChatGPT developed by OpenAI are sampled, and the model is given the prefix and predicts the next token. We update the model parameter so that language models learn to maximize the probability of the correct token, in this case, OpenAI. This process enables language models to encapsulate extensive world knowledge, language understanding, and generation capabilities entirely within their parameters. However, many of us have already noticed significant limitations in current such parametric language models. One of the most well-known issues is hallucination, where the model generates outputs that contain a lot of factual errors. For example, I asked ChatGPT to explain my research and list some of my representative papers. Initially, the model correctly identified me as a researcher working on question answering, which is accurate. However, things quickly went wrong when it started generating list of paper titles. The first papers it mentioned was real, but it's not written by me. Also, the second paper is related to my previous work, but this paper title doesn't exist. As you can see, language models often struggle in long-tail knowledge or knowledge that is underrepresented in pre-training time. How can we overcome such long-tail hallucination? The challenge here is that for less popular concepts, even if they appear pre-training time, language models can't effectively memorize or retrieve knowledge in their parameter. Then what if we could directly search large-scale entire text data used during pre-training time, locate a few documents about rare entities like Akari Asai here, and reason over them to update the answer? This is essentially the core intuition behind retrieval-augmented language models. We found that this could significantly reduce hallucination, even just on top of existing language models. Moreover, retrieval-augmented language models offer many different key advantages over parametric models. Another major limitation of parametric language models is that the knowledge quickly become outdated as the pre-training data is often collected far in advance. Or continuously training model on new data is one solution, but it is super expensive because now the language model training data and size of model is like much larger than previous models we had. As a result, even state-of-the-art models like GPT-4o still depend on knowledge from 2023 or 2024. Retrieval-augmented language models can address this issue by dynamically updating their knowledge via external data store. Instead of retraining huge language models on new data, we can simply replace the data store with a new one, allowing the model to generate more up-to-date responses. We found that this approach is quite effective to enable models like GPT-3 to update their prediction based on even last week's news. Additionally, because now we have this kind of citation or evidence in addition to the model response, it enables us to verify the answers much easily than normal parametric language model, which doesn't provide explanation on why this model generates this answer. And this kind of verifiability is quite helpful, especially for domains where factual reliability is critical. I hope we are now on the same page that retrieval-augmented language models are highly effective for building language model-based systems, particularly when reliability or adaptability are crucial, like healthcare domain or scientific domain. In fact, retrieval-augmented language models are becoming ubiquitous. OpenAI has been releasing a ChatGPT search or deep research system, both of which leverage retrieval-augmented techniques to provide more accurate, up-to-date responses. In today's lecture, I will discuss how we can build such systems. And those products are not only just in OpenAI system, but also many other company products like Google Gemini, or like other search engine system like Perplexity or U.com search. Beyond those user-facing chat applications, retrieval-augmented language models are also widely used across industries to automate core tasks and develop customer-facing products, making them a key component of modern AI systems. So today I will teach you how we can build such retrieval-augmented language models by providing high-level overview of their core techniques. Before diving into the detail of each component, let me provide a more concrete descriptions of how retrieval-augmented language models work. Those models enhance parametric or monolithic language models like GPT-4 or 5 by incorporating a large-scale data store, a collection of documents. Documents lengths are depending on models, but typically each document consists of a few hundred words. A retrieval model identifies the documents that are most related to the input query from the data store. In particular, given the user input X, we use a retrieval system to compute the similarity between query X and documents in the data store to identify the top K documents D with the highest similarity score. Then, we incorporate retrieval documents D to enhance the prediction of language models. Note that there are many different ways to incorporate the retrieval documents D. Today, I will discuss how we can improve each key component of retrieval-augmented language models: the data store, retrieval model, language model, and the integration. First, I will briefly cover data store construction, as the quality of the data store is fundamental to building effective retrieval-augmented language models. I will discuss what type of documents should be included, how we should process and structure the data store, and other important considerations to ensure optimal retrieval performance. Then, I will discuss the different type of retrieval models. Information retrieval itself is a vast field, so rather than diving into all the detail, I'll provide a high-level overview of different retrieval techniques, their training methodologies, and how they are evaluated. Hopefully, this will give you a solid understanding of key approaches used to retrieve relevant information effectively. Lastly, I will discuss how retrieval systems and language models can be integrated, covering different architecture approach at higher level. Then I will highlight some recent advancement in this area, especially focusing on with new models improving retrieval-augmented generation, showing how those new approaches improve the effectiveness and efficiency of retrieval-augmented generation. So now let me start with the data store part, and feel free to post questions in Zoom chat if you have any questions. Okay. First, let's consider what data we should have in retrieval-augmented language models data store. The choice of data store depends heavily on the target application. If your goal is to answer fact-based questions, factored questions, then a widely used and high-quality sources like English Superior is indeed a strong candidate. Many NLP papers use English Superior to enhance the model's prediction in those like fact-based open domain QA type applications. However, if your application is more specialized, such as building a retrieval-augmented system for code generation or code assistant, then you need to be more strategic in constructing your data store. For code-related applications, your sources might include a mix of GitHub repository, official documentation, or community forums like Stack Overflow. The key takeaways from those prior work is that the choice of data store should be carefully aligned with the specific needs of your application to ensure high-quality retrieval and effective system performance. Another approach is you can use massive data store that include everything. We have previously worked on it and built 1.4 trillion token data store, which is close to language models pre-training data scale. We found that this is super effective for both upstream and downstream tasks, as you can see in this chart. If we scale up the data store size in terms of billions of tokens from left side to right side, we can see large performance improvement in terms of language model perplexity and also downstream tasks. But the key challenge here is that having such massive data store could be really expensive, because now we have like tens of millions of video, even billions of documents, and each document will require us to generate embedding. And we need to have massive GPU, CPU, and memory at inference time to ensure like fast retrieval. So there is a trade-off between the scale of data store and also efficiency at inference time. There are many papers that simply use existing production search engine API like Google Search to overcome challenges of hosting massive data store. But if we use those black box API, there are many new challenges. For example, like we cannot reproduce the result, or like those search APIs are primarily optimized for human users, and it's still unclear if those search systems are primarily optimal for language models inference. Once we identify the set of useful documents, how should we process those documents? Even in English Superior, where we can more easily get clean processed documents, there are many open questions. For example, each Wikipedia article is often much longer than a few hundreds or even few thousand words. And if we simply like feed them to like language model or retrieval system, it might already hit the context window. So we needed to process those each articles to a set of documents. Oh, there are many factors to consider. The typical document processing pipeline follows those key steps. First, we create and process data. This involves collecting relevant data or web pages from appropriate sources and then cleaning it to ensure consistency and usability. For instance, we download Wikipedia articles and process HTML to extract the plain text. Then we chunk plain text into documents. Instead of treating entire article as single retrieval unit, we typically break them down into a small chunks to improve retrieval accuracy. A common chunking strategy is just split text into fixed size of segments, for example, like every 200 words. Another approach is semantic segmentation, where we use structural elements like paragraph tags, double new lines, or section headers to preserve more meaningful context segmentation when breaking up documents. After chunking, it's also useful to apply heuristic filters to define the data store. for instance, even in English Wikipedia, there are many articles that don't have any text or like it has like really short text. Prior work found that if we filter out those really kind of low quality or like unhelpful documents during this post-processing stage, we can improve the model performance a lot. So it's important to carefully, after you collect the initial data, it's also important to carefully process the data so that you can get the best of result from those data store. So in summary, in this part, I discussed data store. An important takeaway is to choose the right data store and carefully process those data stores. And scaling data store could be helpful, but it requires additional computational requirement. So I would say like first finding a small and manageable scale of data store is quite important. So before moving on, I can answer if there's any question.
Yeah, so there's a question about chunking.
Mhm.
So does chunking cause the retrieved info to lose key info, such as what document the initial document came from?
Yeah,
Help with citations.
that's pretty good question. So that's actually like a common like failure mode. So what we do typically is that we concatenate the original original website title was this like each chunk document. So like when we use a Wikipedia article, instead of just showing like the 200 words segment of Wikipedia article, we also like give the title information, or some people use the URL as well, so that model know like where this article is coming from. But still, if we use this kind of every 200 chunking, then typically like documents start at the middle of sentence and then like end at the middle of sentence as well. So there are some papers that show that this kind of every 200 chunking could be suboptimal, especially for some applications like scientific research. And that's why, like I say, that semantic segmentation using the document, like more structural information of documents could be helpful. But the challenge is that some websites don't provide those like semantic segmentation unit. So I think in many papers, people typically just use every 200 or every 500 words because it's much easier.
Mm. I had another question about the structured data. So let's say you have like a table of data from Wikipedia, then maybe it's less clear like the best way to represent that, right?
Yeah.
Yeah, what are some different?
Mhm. So right now, I think what we do is that we typically like um almost literally like just chunk based on like every keywords. Um, but as you say, like this could be even more challenging if we have like more structured like table type data. Um, so right now, if people use local data store, I think still like the most popular approach is just using every keywords. But there are many papers that use like external like production API, like search engine, like Google search API or Bing search or like u.com API. And those papers typically like takes the original HTML and then like summarize articles using a summarized article and like generate like markdown document. And these markdown documents typically retain like the original table type structure much better. And so that might be another reason like why those more recent approach perform better than like just using local Wikipedia data store based on like every K token segmentation.
I see. Okay. And then there's another question about images or multimodal content. And how do we deal with that?
Yeah, that's a pretty good question. So I would say still multimodal retrievals are like kind of like underexplored. So they're like a little research on like text-only retrieval side and also like multimodal of like mostly like image or like video retrieval research. But still we don't have really good retrieval model that can bridge multimodal data. So like given the text query, it can retrieve both text documents or like multimodal like image type data, or like given the image, like find a text document or like other like video data and so on. Um, one challenge is that for retrieval training, I will talk about it later. We typically use a pair of query and also positive documents and negative documents. And we also needed to like really carefully choose those positive documents and negative documents. And those are typically based on existing like links between this kind of query and documents. But those are not typically available in like, especially when we try to scale up to like more modalities. So I would say like it's still like work in progress area, and at the same time, it's really exciting field for research, especially now we are kind of like building retrieval-augmented language model system as web agent, and like those system might need to handle with like more like multimodal data.
Okay, cool, thanks. And then there's one more question, but maybe we could save it for the last part. You said you're going to talk about some of the state of the art.
Okay,
So
sounds
someone was wondering like what
yeah.
data stores are used in things like OpenAI or Gemini or Perplexity, but maybe
Uh,
just to keep that in
yeah,
mind, or you can cover it right now.
yeah. A quick answer is that it's increasing number of papers, and I'm pretty sure like industry products now using web search engine like Google Search API. Bing Search like stopped the API, but like some paper also use Bing Search API. And one reason is that now many of those language model based like RAG applications um, kind of focusing on like web browsing tasks or more complex tasks, not only just like answering factored questions. And if the task is just answering like general domain like factored questions, then Wikipedia is a pretty good data store. Well, like when we try to like host retrieval augmented generation system for many different use cases, then like Wikipedia is typically not the like doesn't cover all of the information we need. And so but at the same time, like as I said, hosting like trillion token data store is super, super expensive. So a quick and like simple solution is just use production search engine API. Um, and so I believe many of those industry deep research system use those production API. But I also think that some deep research system combine multiple different search systems, not only just Google search, but could it be like Google Scholar search or like semantic Scholar search for research, or like some kind of code retrieval API for like more software engineering or code generation type task. Um, but those companies don't disclose like what they're doing behind this like chat application. But there are some new deep research papers that try to combine multiple search systems. So that's my guess.
Okay, great, thanks. And thanks for all the great questions.
Yeah. Okay, let me go to the next section. So now let's discuss how we can build retrieval system using data store. As I just discussed, for some application, people use more like production search engine system. But if you have more like specific like focus task, still like building your own local retrieval system could be super helpful. And I heard that like the homework assignment for advanced NLP is to build retrieval augmented generation system for about like CMU like FAQ. So I think for those cases, you might need to like actually build your own local retrieval system. So hopefully this section will help you to learn like how to get started with building retrieval pipeline. The goal of retrieval systems is to identify the most related set of documents to the query. And we typically compute the similarity between query and documents, all of the documents in the data store. And there are many different types of retrieval systems depending on how they compute the similarity. In information retrieval communities, sparse retrieval systems have been widely used for decades. And those sparse retrieval systems typically count word and term frequency in the documents to build index, which doesn't require training. More recently, dense or neural retrieval systems have shown to be more effective. They train neural retrieval models to compute embeddings of documents and query embedding of document and query and compute the embedding similarity in this more denser embedding space. And lastly, those sparse or dense retrieval systems are often combined with reranking models, which compute the similarity between documents and queries by generating query-dependent document representations and compute the final similarity scores. I'll discuss each of them in detail in a minute, but often the cost of those systems increase from left to right, while the performance often gets better. Now let's talk about sparse retrieval system. For sparse retrieval system, we generate embedding of documents and query based on term frequency or word frequency. We start with the vocabulary of words. So here, like we have vocabulary including like what, candy, NLP, is language, like, and so on. And we have 3 documents, and now we have a new query. For each document or query, we build a binary bag of words vector. If a word appears in document, then its entry is 1. If not, it's going to be 0. For example, for this query, for this document, D, what is like, candy is like, then the entries of what candy is and like at 1, while all other words are 0. This binary vector is often called a one-hot or multi-hot representation. But this has a limitation. In some documents, some words appear multiple times, like here, like appears twice in document D1, but this will not be captured in those one-hot vectors. So term count vectors count the occurrence of a word in a document, taking into considerations of such term frequency inside the document. Here, like appear twice, we update the original one-hot vector to 2. Based on this, now we compute term frequency and inverse term frequency. Term frequency compute frequency of term T in the document D divided by the total number of terms in the document. Here, if we consider TF of T1 what given D1, what is like, candy is like, then like we have in total 6 words in D1, while like we have what appear once in this document. So we will get roughly like 0.16 as TF score. IDF, on the other hand, compute total number of documents in the corpus D. Like for example, in this case, we have 3 documents, so it's going to be 3, divided by the number of documents containing the term T. And in this case, the term T is what, and what only appears in 1 document out of 3. And we take the log of this number. So in this case, this term T1 given D1 will get roughly like 1 because like we take log of 3. So as a result, the TF-IDF score of what given those 3 documents is going to be 0.18, and we compute this TF-IDF score for all words across all of the documents we have. And then once we get query, we compute those TF-IDF score for each word in this query, and then we compute the similarity of those sparse embedding. Note that as we consider both TF-IDF score, even the same term can get different weights across documents because the TF-IDF score, TF score changes. For is, we get 0.13 in D1, but we only get like 0.05 in D2. Also, even inside the same document, terms with the same count can get different number because we considered IDF score. In D2, both NLP and language appear once, but language have higher score because this word doesn't appear in any other document, so we think that this term is more important than other terms that appear multiple times in other documents. After we compute the design similarity between sparse embedding, we compute after we construct the sparse embedding, we compute the design similarity between query and also all documents in the data store. When we compute the similarity, in this case, D1 will get the highest score, 0.44. Now, maybe you can see the problem of using such a sparse embedding system. When we look at those 3 documents, in my opinion, D2 or maybe like DC has higher similarity to the question, and especially D2 directly answered NLP is an acronym for natural language processing. But this document got lowest similarity score to the query. This is because one, this kind of term frequency only consider like term level similarity, and it doesn't fully capture like semantic similarity. For example, semantic similarity. For example, like here, the D2 answers the question, but like D1 got the highest score because D1 is also like question and saying like what is like, which is pretty similar to what is NLP. And also these lexical similarities cannot capture like different paraphrasing. For instance, like here D2 say like NLP is natural language processing, but this is not fully captured because we don't register those like paraphrasing well. Another issue is that this is simple bag of words, so we don't consider order of words. So a funny example is that dog bites man and man bites dog look similar in terms of TF-IDF score, which is obviously a problem in some case. So recently, we have observed the neural dense retrieval system can overcome those challenges and outperform stats-sparse retrieval system. The basic idea remains the same. We want to compute query-independent embeddings of documents and then like generate query embedding and compute the similarity based on embedding space. But instead of generating embeddings based on term frequency, now we use powerful neural models to generate dense embedding of documents and query using trained encoder models. Given the encoder model, we pre-compute all of the embedding of those documents, and then given the query, we use the same or different encoder system to generate dense embedding of query. After that, we can compute the similarity of those embedding by performing the first nearest neighbor search to find the top k most related documents. There are multiple ways to generate such dense embeddings. I believe you have learned encoder-only and masked language model like BERT, and one common approach is to take the output representation of CLS token of such models, which is d-dimension float vectors already. Another popular approach is to take mean, max, or average pooling of output vectors for the entire output token sequence. This approach can be directly applied to non-masked language models without any CLS tokens like Llama, and has shown to be quite effective. An empirical comparison of those different methodologies are task-dependent, as shown in the SBERT and SGPT's papers. So if possible, I recommend you to try out different way to pool representations. Also, I'd like to briefly discuss another key element, fast nearest neighbor search. Especially when we scale to large-scale search, like retrieving over hundreds of millions of documents, the efficiency of k-nearest neighbor search is really important. This area itself is another big research topic in theory, machine learning, algorithm, and wider AI community, so I won't go into the detail, but if you are interested, FICE, one of the most widely used libraries in this area, has a really nice overview and implementation of many different types of index. Specifically, if we deal with, let's say, English Wikipedia scale, tens of millions of documents, then you can probably just use float index, which performs exact nearest neighbor search. But if you needed to deal with much larger data store, then another popular alternative is HNSW, which build a hierarchy of indexing to speed up search. But this method requires much larger memory and storage requirement for indexing. Another consideration for practical application is the total size of index. If your embeddings are order of tens of millions, like English Wikipedia, then even with best retrieval models, you end up consuming around 100 gigabyte memory. So to minimize index size, you can also explore quantization or binary embedding methodologies. For instance, we have some prior work that generate binary embedding instead of generating float embeddings. And by doing that, we can reduce the total index size, total embedding size of Wikipedia from 60 gigabyte to 2 gigabyte. Now, I also want to quickly talk about how we train such retrieval system. We typically use a contrastive learning objective. The model learns to put the query embedding closer to its positive documents while pushing it away from negative documents embedding. Concretely, we minimize a contrastive objective that compares a query positive similarity to the sum of query negative similarities. A good encoder system has a high score to the positive document, driving the loss towards zero, whereas a poor encoder assigns high scores to positive, high score to negative, which makes the loss much larger. The key challenge is choosing good positive and negative passages during training time. Typically, we cannot use the entire index during training time because it could be super expensive. So we typically we typically construct a good negative and positive documents pair using a technique called in-batch negative. A core idea is that given the query and also all of the positive documents to those queries in the same mini batch, we use positive documents to other queries as negative for this specific Q1. And this in-batch negative, although the idea is quite simple, has shown to be quite effective to train dense retrieval system. Also, there are some papers that try to do more complex negative document sampling strategy, which we call hard negatives. And the original DPL paper has some discussion on like how we should construct those negative and positive documents. So if you're interested in, please go look at the paper. And there are also like some new techniques to improve the training of retrieval system. In the methodology of DPL, we needed to have query and positive documents pair to start the training. However, when we try to scale up the training, we typically don't have such labeled pair. So there are some papers that tries to scale up those retrieval model training by using unsupervised training recipe, pretty much like language model. So this paper called Contriver has a really nice recipe and like show the effectiveness of unsupervised training. And one of the technique is that they use independent cropping technology where like they extract the sentence from the original they extract the sentences from one document and then like they labeled these sentence pairs as positive pairs because we can assume that sentences from the same document are more likely to be related than the sentence pair sampled from different documents. Contriver, although that was released in 2022, still remains one of the strongest model in like smaller retrieval language models, smaller retrieval models. Another popular techniques in this retrieval area nowadays is doing instruction tuning for retrieval model, like language model instruction tuning. Initially, retrieval system are typically designed and trained for different retrieval use cases. Like we have different retrieval system for Wikipedia, code retrieval, or like FAQ retrievals. However, there is a trend of new retrieval models that can perform those many different retrieval tasks by taking instructions in addition to the original queries. The core technology to make it work is to design good hard negative sample so that we can encourage the model to use those additional task instructions. Lastly, I'd like to briefly mention reranking models, which often give us significant additional gain on top of sparse or dense retrieval models. In sparse and dense retrieval models, we compute the similarity between query and documents based on embeddings, which are computed completely independently. But this doesn't let us to capture like more complex interaction between query and document. So the idea of close encoder is to encode question and document jointly using encoder model, and then like classify or compute the relevant score based on this joint embedding. Now we can generate representation fully conditioned on query. So as you can see, like there's much more interaction, and we found that this kind of a close encoder could be quite powerful on top of existing sparse and dense encoder based models. And now like I would like to briefly talk about how those different retrieval models perform. But before talking about the result, let me briefly recap metrics because we also needed to understand metrics to understand the model capabilities. And I will not dive into how each metrics compute the performance of different models, but I would like to highlight that there are like two major categories of retrieval metrics. So one is unlinked retrieval metrics, which only consider if positive documents appear in like top K retrieved set. but it doesn't consider like any ranking. Another set of metrics consider the ranking of retrieval set. This is important, like if we have to like present the best result in the top result, or like we wanna like make sure like the top results are all related. Well, like, so it depends on like which metric you should pay more attention to is depending on like the application you have. But typically like NEDCG at 10 is widely used in common benchmarks like beer. And if you're interested in, please go look at some textbook or like website that discuss like how we compute those metrics in retrieval task. And let's wrap up this section by introducing a few core benchmark in this area, because those benchmarks help you to pick up like which retrieval system you have to use. One of the most common benchmark in retrieval area is beer, which tests the retrieval model's capability to perform retrieval task in more like zero-shot setup. So in beer, they combine many different kind of like retrieval tasks across many different domains, and then like they test the retrieval performance based on like NDCG or like some other retrieval common retrieval metrics. And when we look at the model performance on this beer benchmark, we can clearly see like some why like existing close encoder-based reranking or unsupervised training is effective. So this is a result from the original contributor paper, and they have some like comparison between different baseline. And as you can see, by adding by adding cross encoder on top of BM25, we can see massive improvement from the original BM25 only result. This result shows that like using reranking model is quite helpful. But interesting finding from the RIA paper and also contributor is that DPL, which was state of the art back then, struggle a lot in this VIA setup. And what people found is that those neural retrieval systems, depending on supervised training, often struggle to generalize to new domain. So we have to like collect supervised training data to make those neural retrieval models work. So the contributor paper showed that we can overcome this issue by doing large-scale unsupervised training, and the contributor paper achieved the best performance back then in this peer benchmark. The most recently, the popular benchmark is the MTEB benchmark, which combine many different embedding-based tasks. So it includes beer as retrieval benchmark, but also like many different other tasks like cross-clustering or classification tasks. And I believe this is one of the kind of like de facto standard leaderboard for embedding tasks nowadays. So whenever like people ask me like, oh, which embedding we should use for our application, I recommend people to take a look at the leaderboard of the MTEB benchmark. And you can go to the website and see like which model performs best across different tasks. But one thing I want to highlight is that now most of the state-of-the-art models are those instruction-trained retrieval models, and they can perform many different tasks without training a single retrieval system for many different tasks. But one thing we needed to be careful about is that those powerful state-of-the-art retrieval systems are getting much larger than the previous retrieval system we had. So contributor or DPL are like just bird-based model, which is just like 100 million parameters. So the embedding size is also like just 768 dimension. So the total index size is pretty small. But when we look at those 7B or like even 4B language models, they have much higher number of embedding dimension, meaning that they consume much more storage and CPU memory at the inference time. But as you can see, those much larger retrieval systems can achieve higher performance. So there is a still trade-off between efficiency and performance of retrieval component. In summary, this part discussing different type of retrieval models, how to train them, and their evaluation metrics, as well as efficiency and performance trade-off. And I'm happy to take questions before moving to the next section too.
Yeah, thanks. So there's one question, and then I had a couple of ones. So first, for the trade-offs between TF-IDF and its retrievers, so you mentioned it a bit on this like beer benchmark, but could you also talk through, yeah, some of the other trade-offs? And I think the question here was like, if you go to a really large scale, like the internet,
Yep.
is one better than the other?
Yeah, it's a very good question. So there are some advantages of those sparse retrieval system. One big advantage is like OOD scenario, and the VIA paper showed that BM25 is actually like more capable than neural retrieval system when we don't have any training data, as I discussed in the slide. Another benefit is that typically this sparse retrieval system is much more like efficient and scalable. So for the OpenScatter demo we had is uses kind of a combination of sparse retrieval system and small neural retrieval system. Because for OpenScatter, we needed to deal with 45 million scientific papers, and we chunked those scientific paper into paragraph level. So we had like hundreds of millions of documents, and we found that it's really hard to we can build dense retrieval system. And for the reason paper, we had like dense retrieval system, which we host locally. But for the public demo, because we needed to handle many user queries at once, we decided to use the combine this sparse retrieval system with small dense retrieval system to make sure like it's scalable enough. So there are some advantages of such sparse retrieval system.
Okay, great, thanks. And yeah, I think in the homework, students will have to explore both, but
That's
also
good.
learn more about it there. There's another question that just came up. So could you re-explain why the instruction-tuned retriever is able to generalize quickly to unseen tasks? Does it
Yeah.
somehow leverage unsupervised data, or how does it do that?
So for instruction tuning, for retrieval model, it's pretty similar to how we do instruction tuning for language model. So we construct a bunch of instruction query and positive documents pair, and then at training time, we concatenate instruction and query, and then do the normal contrastive learning objective. And for our paper, we use Contriver for base retrieval system, and we found that those trained instruction tuned models are good at identifying or like good at like changing its behavior based on instructions. But we found that like the capability to generalize completely new behavioral task is slightly limited, or like the ability to follow complex instructions. Although like still the model perform best in the same size of like different retrieval system. And there is some follow-up work that tries to improve instruction following a retrieval system, and they found that scaling up or using pre-trained language models like 7B language model, 4B language model as the base of retrieval model helps a lot to generalize to more complex or like new retrieval task. So it seems that the model can use those pre-trained knowledge from like language model well if we scale up the retrieval system. But the challenge is that for retrieval, scaling the encoder model could be even more expensive than just like scaling language model part. So that's why like there's a trade-off between efficiency and performance of retrieval models.
Okay, cool, great. Yeah, I had a question kind of on a similar, which is, so in the course we talked about retraining and then fine-tuning. So do we have the same, maybe it's a simple question, like do we have the same setup here where you do massive pre-training and then fine-tune for your task? And then is the pre-training like specific to retrieval, or can you use like language modeling pre-training?
Yeah, so Contriver did kind of continued pre-training where like they take existing like bot-based pre-trained language model, which is already like kind of trained on massive text data, and then like they conduct a contrastive objective-based unsupervised training, which I kind of consider like continued or second stage of pre-training. And after that, they did supervised training using large-scale supervised data like MS Marco. And I think the instruction tuning of those retrieval system is like another stage of fine tuning where like we train the model using a lot of like multitask, essentially like it's just like multitask training of retrieval models. So the trend is like really similar to language model where we do pre-training first and then we do some additional continued pre-training or like just take this pre-training models to do supervised more like task specific training first, but then like people later realize we can also just do like multitask training with instructions. And we got like a lot of inspiration from language model community as well.
Yeah, okay, thanks. And then one other thing came up which might be relevant for like the homework or in practice. I was wondering, Do you usually have to spend some effort in practice to come up with a good query? Because we've been talking about like similarity between query and document. But then like how do you decide what the query is in the first place?
Yeah. So earlier studies usually like just take the original input, users' original input as like search query in like NLP community. But like there's a rich literature in like more like information retrieval community where like people transform what's original query to be like more informative or like more descriptive so that we can maximize the effectiveness of retrieval system. So instead of just using the original query, they transform the query uh based on like using language models or like based on like the first retrieved documents and then like improves the query based on like those retrieved or like other knowledge. And this has shown to be quite effective, especially when the original queries are kind of underspecified or like they are underspecified case. And so I believe that this would be quite effective to improve the retrieval model, to improve the retrieval performance, especially for like more specialized area, like the homework.
Mm. Okay, great. Yeah, thanks. That's all the questions here.
Okay. Yeah. Okay. Now, yeah, let me go to the final section. And here I would like to talk about how we integrate retrieval model and language models to build the final end-to-end retrieval augmented generation system. So there are many different architecture of retrieval augmented language model, and retrieval augmented generation is actually like just one of those many different retrieval language models. And so to understand those different type of retrieval augmented language models, I want to highlight three key aspect. The first one is that what we should retrieve. Given the query, as I said, one of the common approaches is to retrieve text chunks or passages, like the paragraph from Wikipedia. But there are many different units. For example, we can directly retrieve next token, or some people try to like retrieve like different units, like entity or like sentence. And also how often we retrieve is important decision point. Earlier studies often just retrieve once using the original user query as retrieval query. But this is becoming like more problematic if we have like much more complex scenario where like we needed to retrieve multiple times. Another extreme strategy is like retrieve every single token. And there are some papers that indeed retrieve like retrieve for each next token. But this could be quite effective. This could be quite expensive. So there are more papers that try to do more kind of like between those like just single retrieval and like every token retrieval and like makes the model to decide when to use retrieval. And I will discuss it in the next in this section. Once we retrieve documents, the question is how we should use those documents during inference time. Retrieval-augmented generation simply take those retrieved documents in input space by adding like retrieved documents to the original input query. But there are other approaches. For example, some people directly manipulate the output token distributions using retrieved distribution. Or there are some papers that tries to incorporate retrieved documents in middle layer. So I would classify those different retrieval augmented language models into three different categories. The input augmentation is like retrieval augmented generation scenario where we simply append retrieved documents to the original input. And the intermediate fusion, means that we incorporate the retrieved documents in intermediate or the hidden layer of transformer log. And the last one is output interpolation, which we directly manipulates the output token distributions. And today I will mostly focus on input augmentation, but towards the end I will briefly mention this intermediate fusion approach and also output interpolation approach. Well, let's talk about the input augmentation, which provides the foundation of modern retrieval augmented generation system. So given the retrieved documents and the original input, what we do in retrieval augmented generation is pretty simple. We concatenate retrieved documents, and then we append those retrieved documents to the original input, and we feed them together to language model. So now we just change the input space, and we don't need to change the language model itself, and we can take any existing language model to build this retrieval augmented generation system. And those simplicity make people to apply those retrieval-augmented generation system, the retrieval-augmented generation approach to many different models. But initially, when people propose this retrieval-augmented generation models, people typically train retrieval model and language model to improve the performance on downstream tasks. Audio papers like DLQA or like DPL train retrieval models or task language model or like question answering models completely independently. But this doesn't let us, but if we train those models completely independently, each component is not really optimized for like this retrieval augmented generation scenario. And they found that many papers found that even if we take the best retrieval system, those best retrieval systems are not always giving the best end-to-end retrieval augmented generation performance. So to ensure the best performance or like improve the interaction between retrieval and language models, some papers also explored sequential training. So the core idea is that they first train one component first and then use this component to improve the training of the other component. Lastly, joint training is another approach. Here we try to learn retrieval model and generation model together under a single objective. This couples the two modules most tightly and can yield the best end-to-end performance at the cost of a lot of engineering complexity. So how do we train those models in an end-to-end fashion? I'll explain it using retrieval-augmented generation, the Meta's original retrieval-augmented generation method. In RAG, we minimize the negative log likelihood of the predicted answer y given x, just like standard language model training. The key difference is that now the generation is conditioned on retrieval documents. The RAG probability combines the retrieval score, and generation score. So given the input query, a retrieval document, and the model predict tokens, then like we BAP propagate not only to the generation model, but also to the retrieval encoders. A major challenge is that whenever we update the document encoder, we need to refresh the document embedding, which can include like millions of or tens of millions of documents. And this could be quite expensive. Like we don't want to spend like 1 hour to refresh embedding for each training step during SST. So I won't go into the detail, but in this literature, people improve efficiency of this end-to-end training by using some technique like approximate the async update, where we only update embedding an index for every like thousands of steps, or like another approach, try to approximate this hood index update by generating a high quality question and mini-batch negative sample pairs. However, starting in 2022, several papers show that without additional those complex training, strong language models can effectively use retrieval document and reach high performance, matching much smaller but fully supervised models. So one of our papers conducted one of the early study of this simple retrieval augmented generation strategy, and we found that by combining GPT-C with off-the-shelf retrieval model like BM25 or Contriver, we can get performance improvement, especially for long-tail questions. So here we show the model performance on question answering dataset, where we have different level of concept popularity. And the left side shows less popular questions or long-tail questions, and the right side shows more popular questions. And as you can see, the red line, the GPT-C without any retrieval performance, is constantly worse than the retrieval augmented generation performance, indicated as green line. We found that even without training, those retrieval augmented generation can give us huge performance improvement and reduce hallucination in long tail. But such training-free approaches back then also showed many limitations. Those simple RAG methods always retrieve fixed number of documents, regardless of whether external knowledge is needed or not, lacking flexibility. Furthermore, we found that those unnecessary retrieval can easily confuse language model, even when the model originally knows the answer. For instance, given the question, who is Sam Altman, maybe retrieval system fails to retrieve correct document about some Altman, and it can retrieve document about some Adams. A language model are not good at detecting those unhelpful documents and can easily get confused by those unhelpful documents. We found that in most popular questions, this happens more frequently because language models already know the answer. But because of those retrieval errors, language model performance can get worse, and they start generating incorrect answer. Also, there are some other limitation of those simple retrieval generation scenario. Many papers found that even when models cite some additional documents, the model answers are not fully supported by those documents. And this is even more big, serious problem compared to just parametric language models, because now those model responses come with citation, and people kind of assume that those model responses are fully supported by those citations, but it's not true in many cases. Another common issue is that now we retrieve documents and then we take those retrieved documents in input space, which quickly increase the latency of those retrieval-augmented generation models compared to the original parametric language models. So there is a trend of training new language models that can more effectively incorporate those retrieved contexts or new inference time techniques. One of such work, Setterfag, trains language models to decide when to use a retrieval and given the retrieved result, judge whether documents are related, and then finally generate responses based on retrieved documents, providing accurate citation. So given those input, the model first predict if retrieval is needed, and if the retrieval is not needed, then the model acts like a standard language model. But if the retrieval is needed, then we trigger retrieval system to identify a small set of documents. Instead of just taking all of those retrieved documents, the model first evaluates if each of the document is related to the question or not, and then only use the most related document. After that, the model generates response, and after generation, it also evaluates if the generation is fully supported by citation or not. To achieve this functionality, we train language models to generate with special tokens. And if the model generates, for instance, retrieval token, we prompt retrieval models. We trigger retrieval models. And we use those special token approach to evaluate which document is most helpful, or if the model answer is fully supported by citation. Here's one example. Given the query, the model first generates retrieve token, and then retrieval system returns a set of document. Instead of concatenate all of the documents and generate based on this concatenated document, we process and generate responses based on each document in parallel. The model first generates continuation of those continuation given those documents. For the first document, the first document is not super related to the query because this one only talks about language models application in industry. And if the response is based on those unhelpful documents, the information, the continuation is likely to be incorrect, or at least citation is not helpful. So we discard these responses based on unhelpful or irrelevant documents. For the bottom two documents, both of them are related, so the model generates relevant token first, and then start generating responses. After generation, we also make the model to generate judgment on whether the model answer is fully supported by citation or not. In this case, the bottom document is only partially supported, so the model generates partially supported token. We take the best continuation based on special token probabilities so that we can consider both citation relevance and also like whether the model generate fully supported sentences. And we continue this process until the model finishes generation. We found that this approach can significantly reduce the unnecessary retrieval and also make sure the model can generate sentences that are more supported by citation. While Setterfag directly teaches its model to generate with special tokens, concurrent work back then explores alternative approach, which directly generate tool calls or API calls. The tutor format paper is one of the earliest work that teaches language model to generate tutor codes, including search, calculator, or machine translation system, which inspired a lot of follow-up work in tutor-augmented or API-augmented language models. Lastly, I want to also highlight a new trend, deep research system. Those models share the same spirit of a set flag or tutor format style approach that adaptively issue tutor codes to incorporate those new tools at inference time. But the key difference is that they now pair this approach with powerful reasoning language models that can explicitly generate high-quality think and plan tokens to improve predictions. This is an example from such recent like deep research paper, WebThinker, and as you can see, given the original question, the model first generate thinking token and say like, oh, this is a search plan, and now I start searching. And then the model generate the tutor code to trigger retrieval system and takes the retrieval documents in inline, as in set a flag. And after that, the model repeat this thinking, tutor code, and search output activities until it collect all of the information and start generating answers. And those deep research system has shown to be quite effective. And many of you might have tried those like industry deep research applications and you can take a look at those reasoning traces and like those models generate inspection or like planning of those search strategy. So far, I just focused on retrieval-augmented generation. And those methods are again super powerful and providing backbones of many widely used applications. However, those models have many core limitations too. For example, we have to incorporate retrieved documents in input space, so it's not really scalable if we want to deal with like many documents. Like for instance, if we have hundreds of documents in input, each of which have like 1,000 tokens, then it's already like exceeding context window for quantity. Also, even though we take those documents in input space, it doesn't strictly guarantee that the model answers are fully supported by those citations. Although methods like Certifag can address those challenges to some extent, still like we don't have like clear attribution for each token or phrase level. So now let me briefly talk about two different approaches or like alternative architecture of retrieval-augmented language models that address those challenges. So one approach is intermediate fusion, which take many retrieved documents in intermediate space. And so in this retro paper from DeepMind, basically like can change the original transformer block to have a new chunked cross attention layer. So this one is between like set of attention and field of network in each transform block. And by adding this new block, they can take many retrieved documents as embedding to enhance the hidden representation of those model predictions. And they found that this approach enables us to scale up to many documents much more easily. And they also found that by scaling documents, the number of documents used during inference time, we can improve the model performance. But the challenge is that now we change the original architecture of language model from transformer to completely new architecture. So we have to pre-train language models again. And so there's a follow-up work based on instruct retro using Llama. And although like they only require continued pre-training, still it's super expensive, especially for academic scale. And also it's still unclear like if this completely new architecture can be helpful in terms of downstream performance. So compared to retrieval-augmented generation, still those intermediate fusion is less widely used. Lastly, both input augmentation and intermediate incorporations don't strictly guarantee that model responses are based on those retrieved documents. So there's another approach called output interpolation, which directly manipulates the output token distributions and can give even like token level attribution of model output. Kernel language models is one of such approaches. So the core idea is to interpolate output token distribution by taking a weighted sum of two parts. The first one is parametric distribution, which is directly predicted by language model as a normal language model prediction. But the other distribution is a non-parametric distribution, where we build by retrieving similar context from large-scale training data, measuring their similarity to the test context, and using those similarity to score the next token. This method doesn't require additional training. And as you can see, as you increase the weight of those non-parametric content, each predicted token becomes more strictly attributed to specific sequences in the training data. However, prior studies also found that those Canyon language models often underperform standard language model, so more work is needed to validate and improve this approach. To summarize part three, Retrieval-Augmented Generation is most widely used approach for retrieval-augmented language models, and it works well in practice, but has clear limitations. Grounding isn't guaranteed, and performance also pretty much depending on retrieval quality. So I reviewed some of the recent progress addressing those challenges, and we also looked at alternative architecture that integrate evidence at different stages, like intermediate incorporation and output interpolation. So this is pretty much all I wanted to talk today, and now I'm happy to answer questions.
Okay, great. Thank you. We have one question, and please feel free to add more because we have a few minutes. So the first one is on the topic of to retrieve. So you mentioned even like retrieving for every next token. So the question is like, how do you implement that? Or maybe another question would be like, what is typically done in practice?
Yeah, so when I say like retrieving like every single token, it's pretty much scanning language models where like for each next token prediction, they compute the similarity between like this test context, which is basically like the preceding generation, and then like they find similar context in training data, and then like they basically like takes the target word of those similar training contexts as a next token prediction. Another like adaptive approach is like set-flag or like those like two format type approach is more like adaptive retrieval strategy. And for that, they retrieve like multiple time during generation, but typically like they insert those two code like for like sentence level or like each semantic continuation level. And so it's still like it still help us to retrieve more information as we generate more, but like the frequency is much lower than like token level retrieval. And I think this adaptive retrieval approach is a like nice middle ground between like just single time retrieval or and every token retrieval.
Mhm. Thanks. And then there was maybe a follow-up question, which if you look at what's being done in industry now or a standard RAG pipeline, what would they typically use?
So the deep research like language model part or retrieval part.
So the question didn't specify, but maybe or well, like you introduced the next token retrieval or retrieving once, what would be the kind of standard pattern?
Yeah, I think my guess is most of the industry deep research system is pretty much retrieval augmented generation system. And right now, the deep research application, um, I assume like they couple reasoning language model with those search tools. And when you look at the Gemini deep research or like OpenAI deep research traces, the model typically generate like, oh, like this is my plan and this is my tool, this is my like search code. And then like based on the search, this is the information we have so far, and like let's go to next query and so on. And I believe that it's basically like they take the best language model they have in-house and then like couple it with those tool augmented approach. And to do that, many industry like frontier models are now train those models with tools as part of their post training. So when you look at the DeepSeek 3.1, they have like specification that like those models are trained with search and also Python interpreter. So you can like use those tools just like out of books by using those language models. Um, there are some papers that use more innovative architecture. For example, Google has a new paper which use diffusion model for deep research. And I think the idea is really cool because diffusion enable us to like do more like because deep research we typically have like much longer context, and also like we want to like edit like those model responses or like search result at middle generation instead of just generating from left to right. And using diffusion makes much sense, but I think still it's kind of like one of those pilot study, but it's not the most de facto standard approach as of now to build those deep research system.
Great, thank you. And there's another question about building a RAG system. So when building a RAG solution to address a particular use case, what are the top considerations for maximizing performance?
Um, so I think identifying good data store is actually important, or like identifying good data store and also the search system we should use for different downstream tasks. So right now we are working on building deep research system, and what we found is that if we only text model for general domain factored question like browser comp, simple QA, then like we can just use um like Google Web Search API as retrieval system. But we also did evaluation on like many different setup, like healthcare domain or like research domain. And for instance, with research domain, if we only use those web search system, it's not enough. And we found that the best performance comes when we combine those deep research system with like Semantic Scholar API or Google Search API, which is more specialized for research domain. Um, Building good inference pipeline is another important part, but I think it's basically like all the part is pretty important, like how we build a data store, which retrieval system we want to use, or like after retrieval, like which ranking model we want to use, and then like how to combine them at the inference time. So I recommend like exploring different approach for like each component.
Okay, great. I think that was a great question maybe to end on. I think we're out of time. So